Hi. We will start by asking the question whether Simulink can solve differential equations. To answer this question, let's start with a simple equation with a known solution. The equation is the second derivative of an unknown x with respect to time is equal to minus x. The general solution is x equal a cos t plus b, where a is the amplitude, t is the time, b is the phase. To find the solution on Simulink, the question to be asked is, what is the function x if differentiated twice gives minus the same function? The reciprocal is what is the function that is when it is integrated twice gives minus the same function. As we will see, working with integrators is better than working with differentiators. To ease the use of Simulink, MathWorks proposed a very rich library full of various blocks that perform different jobs. Well, most of the tasks to solve any problem, in fact, is to spot the right blocks to use and graphically interconnect them. To solve our problem, which is solving the aforementioned equation, double dot x equal minus x, we need a block to perform the integration, a block to multiply by a constant. Here we will use a gain of -1, and an oscilloscope to display the results. Well, we will start by starting from MATLAB Simulink. Okay, this is Simulink. Actually, we could write it down, but here we have a button, Simulink. We will start by a blank model. And we click on Library Browser. We said that we need an integrator. In fact, here we have commonly used blocks, and somewhere, here you are, I can see integrators. So to use this block, actually what we could do is drag and drop, or we could, for instance, right click and then choose add block to model, and the last option is to select the block and type Ctrl-I. The blocks are objects, therefore they could be copied and pasted. Ctrl-C, Ctrl-V. So I'm going to wire the blocks to express the equations. I will assume that on the left side I have an acceleration. After integrating the acceleration, I have the velocity. So I will connect these two blocks, and the output after integrating the velocity is the displacement. So I will connect this block to the gain, and I will change the value from 1 to -1, and the output will be feedback to the origin. I think I need to flip this block. Here we are. So the acceleration is integrated to give velocity. The velocity is integrated to give displacement. The displacement now minus displacement is equal acceleration. So the equation is checked. The oscilloscope has an input. The input I will display displacements. So to start this simulation, I will double click the scope and click on the green button. Well, what I get, in fact, it's not surprising. The solution is zero. In fact, by default, the integrator calculates the integral assuming a zero initial condition. Therefore, our situation is as if we integrate from rest. So x0 equals 0 and v0 equals 0, the acceleration, and the solution is x equals 0. In order to solve this problem, in fact, we need to change the initial condition. To do so, I will double click on the integrator, and here we are. We can see that in this the initial condition is 0. I will start by changing the initial condition source, and I will put external. External means that our block has an extra input which I can use. I will click on the library browser and look for constants. Here we are. I will put the constant on the model and connect my constant to the first block, the left block, meaning that what is the solution of double dot x equal minus x if v0 equal 1 meter per second. To find the solution, I double click on the scope and run the simulation, and here we are. We can see that the function sine t is the solution. We could also, to verify this, in fact, add the velocity. I will start by changing the number of input ports, and I choose 2. Here we are, we have an extra port. I will drag the input and choose the wire between the two integrators. We said that here we have an acceleration, so the speed or the velocity is between the integrators. I go back to the oscilloscope and start the simulation, and we verify that in fact the blue curve, which corresponds to x, it's the sine wave, and the velocity is the cosine. Initial velocity is square root of 2 cos t minus p over pi over 4. Let's check this. The amplitude is checked to be, is verified to be square root of 2, 1.4. And in fact, the maximum occurs for t equal pi over 4. Now, what about if we forget and we use a gain of 1 instead of -1, meaning that the equation to be solved is double dot x equal x. And we know the solution. The solution is a constant exponential t. And the v is also the same. We start the simulation, and what we will see is that we have two curves which are superimposed. To check this, in fact, I can separate the two traces, and here I have the x, and below I have the velocity, and I check, in fact, the solution is a constant which depends on the initial condition, exponential t. That's it.